Hey everyone, today we're finally going to learn some shortcuts for taking the derivative. Okay. And this first one is one that we'll actually probably use the most this quarter, and it is called the power rule. And so if we want to differentiate something that is x to some real number, well, its derivative is n times x to the n minus 1. There we go. And we're going to go ahead and actually prove this. Okay. We're going to use our limit definition of the derivative to prove this. So let's start off with that. So we have the limit as h approaches 0. And now if f of x is equal to x to the n, then I'm going to have x plus h to the n minus x to the n. And then this is all over h. And our next step is actually going to be the most, probably the scariest looking step. And is what we're going to do is we're really just going to expand this x plus h to the n. And I'll explain a little bit where it comes from here in a second. But if we start expanding that out, it's going to wind up looking like x to the n plus nx to the n minus 1 times h plus n times n minus 1 over 2 factorial. And actually, I'm just going to write that as 2. I don't want to confuse us. Over 2 x to the n minus 2 times h squared plus, and there's going to be a bunch more terms, and we're going to keep following this pattern, and then we'll end up with n x h to the n minus 1 plus h to the n. And then this is all minus x to the n. And then this is all over. Maybe I'll use this line tool. Here we go. And this is all over h. And you might already see that we're going to have a couple terms cancel out. It's x to the n and minus x to the n. But you also might be wondering, again, how did we do this? Where on earth did this come from? So if you want to look into this a little more, it's called the Binomial Theorem. All right, let's take this another step further. So notice that out of all the terms that are left, notice that they all have h's in them. So we could factor in h out of the terms that are left here, and we could cancel it with this h that's down here, but I don't want to do that all at once. So let's factor out that h. So this is going to give us an n x to the n minus 1 plus n times n minus 1 all over 2 times x to the n minus 2, and then times h, and so on. And once we get to the other end of this, it'll start looking like n x to the h, or n times x times h to the n minus 2, because we're taking an h from it, and plus h to the n minus 1, and again because we're taking an h from that. And then this is all over h still. All right, and h over h is just 1, so we can cancel those h's. And actually, after we do cancel those h's, I want you to note one thing about the remaining terms that are in the parentheses there. One of them does not have an h, the rest of them do. Okay. So I can actually break this into two limits if I want, right? We can split up. If we have the limit of a sum, we can split up that sum and take the limit of each of the two parts separately. So let's do that. Let's do that with the nx to the n minus 1, and then with the rest of the terms. And so the rest of our terms looks like n minus 1, all over 2, x to the n minus 2, again, times h. And these middle terms that I'm leaving out, they're going to have an h squared, an h cubed, and so on until we get all the way to the end here, which is n xh to the n minus 2 plus h to the n minus 1. And now I want you to notice, I guess I've already asked you to notice this once, but we have a bunch of h's here in all those remaining terms. And h is going to go to 0. So all these, this limit here on the right is going to go to 0, while this one on the left, it doesn't have any h's in it. So this limit is just n x to the n minus 1. Okay, and we've done it. We've proved the power rule here, but not in its full generality. So again, we've only proved this for positive integers. So that means if n is a number like 1, 2, 3, 4, 5, this does not include actually negative numbers here, or maybe like n equal to 1/2. That's not included. But we will be able to prove that once we get a little further into the quarter. But we will just use this for now without proof that this works for real number exponents, not just integer exponents. Next on our list, we have something a little easier. We are going to look at the derivative of a constant. Now, we could technically actually figure out maybe what this is using our power rule, but we haven't proven that general version of the power rule yet anyway. And this is going to actually be pretty easy. So if you actually have a function that's constant, then its derivative is just 0. And we could set this up. We could try and find f prime of x, and this would be the limit as h approaches 0. And I'm actually going to write in here f of x plus h minus f of x all over h. And next, we'll have the limit as h approaches 0. And now, remember, f of x is constant, so f of x plus h should be equal to c, and so should f of x. So we end up with here 0 over h, which is just 0. And so if you take the limit as h approaches 0 of 0, we just get 0. All right, now we want to try and apply these new rules here. So I'm going to put actually our power rule over here. So if you were to differentiate something that looks like this, x to the n, we'll get n times x to the n minus 1. All right, so if we do that, here in this question, n would be 7, right? So f prime of x is I'm going to write 7 first, x, and then to the n minus 1. So if you take away 1, that's 6. And that's it. All right, to approach the next one, notice we actually have something that is not of the form x to the n. But maybe we can make it that way. Remember, this x here is technically, right, x to the 1. And this cube root of x is technically x to the 1/3. And if we add their exponents, we'll get x to the 4/3. Right? But this isn't our answer. We just now have it in this form. We still have to take the derivative. All right, so we'll bring this down to 4/3. That's our n, 4/3 x. And then if we were to take that 4/3 and take away 1, so 4/3 minus 1, let's actually write that in here. Right, we're going to get 4/3 x to the 1/3. Okay, or if we wanted to rewrite this a little bit, we could rewrite this as 4 times the cube root of x all over 3. And the main idea that I was really using in this problem that maybe you would like a refresher from algebra or pre-calc is that if you were to take the nth root of some number, that's equivalent to x to the 1 over n. All right, on to another one. So notice again, this is not of that form up there, x to the n, but we can make it that way. Right, this is really x to the minus 2. And so now if I want to differentiate this, and maybe let's use a different notation this time. How about dh dx? So n is minus 2, so we'll bring down that minus 2, x. And then if you subtract by 1, we'll get negative 3. And so there's our derivative. And then we have one more here. And this one's actually meant to almost, I don't want to call it a trick question, but it's meant to make sure that we understand the power rule. So if we were to differentiate, and I know that this formula is right up above, but I want it in front of us. So if we differentiate with respect to x, something that's of the form x to the n, this is the result, okay? Well, if I were to differentiate this one with respect to x, well, there aren't any x's in this equation, right? Pi is just a constant anyway. So this derivative is 0, right? Pi to the 4th is a constant. Maybe let's write ourselves a little note here. I'm going to get rid of this though.